Hello everyone, welcome back to the fifth lecture of the last week of week 12, and this is the last lecture for the whole course of introduction to single variable calculus. I believe that we had explored from starting from the functions and definition of the functions to this stage, and it will take at least 12 weeks to me as well as you to come at the end. So now one thing in a curve tracing and asymptotes has been left, that is the polar coordinates curve tracing. So any equation which are given in a polar form can be curve traced using the simple methodology. Now we had explored for a coordinate geometry. Now it's a time for Cartesian coordinate, and now it's a time for the polar coordinates. So look at the picture. Picture itself says how you have transformed the Cartesian coordinate to the polar coordinate. So putting x equal to r cos theta, y equal to r sin theta, x square plus y square equal to 1, r square, and tan of theta equal to y by x. That will gives you a transformation from a coordinate axis to the polar axis. And in the polar axis, look at this one. The O, the origin, now denote the pole, and the x-axis, that means the axis passing through the pole is called polar axis, and the angle of any radial axes are called theta, and the any point P has the radial length that is called r. So this is the radius, this is theta, and theta has been measured in anti-clockwise from the polar axis, and polar axis was a straight line passing through the pole itself. That's clear? And so now we shall consider the problem of tracing those curves whose equations are given in a polar form. In such coordinate system, we can associate each point P here, see here, by how much the radial distance it has and how much the angle it has. So there are two polar coordinates needed, r and theta, where r is the number of units between P and the pole. Pole is here, origin, and theta is an angle from the polar axis to the ray OP. So between the ray OP, right? And if r is negative, the point is located on the opposite side of the origin. So I mean something, if here any q is located here, so that means what? That means this angle is taken like this, anti-clockwise from the polar axis. So as you can see, the angle increases and then it will leads to you the negatively situated the point. So q is here, right? So for polar equations, the curve tracing depends on some of the peculiar behaviors. One of the more property is the symmetry one. As we have seen that any function in a Cartesian coordinate may be symmetrical about x-axis, may be symmetrical about the y-axis, and may be symmetrical about the origin, or may be symmetrical about x equal to y, any line, right? Here for the symmetry we use the r and theta. So we will have 3 or 4 different type of the symmetry. That is, either it is symmetrical about theta equal to pi by 2, or theta minus of pi by 2, or it is symmetrical about r, and so on, right? So if the equation remains unchanged when theta is replaced by minus theta, then the curve is symmetrical about the initial line. And what is your initial line? Initial line is this one, right? If the equation does not change when r is replaced by minus r, then the curve is symmetrical about the pole, the origin. Origin, have you seen here? This one, this is the pole. So if r equal to minus r, then it is symmetrical about the pole. If theta equal to minus 10 and remains unchanged, that means it is for with the initial line. So this line about it is a symmetrical one. And finally, if the equation does not change when theta is replaced by pi minus theta, see, theta is replaced by pi minus theta, then the curve is symmetrical with respect to the line theta equal to pi by 2. That's what we had calculated, and theta equal to pi by 2, that means like this type of things, right? So it is symmetrical about this line when we have changes theta to pi minus theta, right? So three things we had here, remember. First one was theta is replaced by minus theta, that means symmetrical about initial line, and r is equal to minus r, second one, then symmetrical about pole, and the third one that is theta is replaced by pi minus theta, then it is symmetrical about theta equal to pi by 2. That is the three things, right? Now find out the reason where the permissible values of theta may be permitted, right? So find the limits within which r must lie for the permissible values of theta. And if r is less than a or r is greater than a, for some a is greater than 0, then the curve lies entirely within or outside the circle depending on r is less than a and r is greater than a. Circle r equal to a. If r square is negative, for some values of theta, r is negative, not the r square, right? Then the curve has no portion in the corresponding region. This is the r only. Angle between the line joining a point of the curve to the origin and the tangent. So now we have a third property which we are going to investigate, is angle between the line joining a point of the curve to the origin and the tangent. So at suitable points, this angle can be determined easily, right? It helps in knowing the shape of the curve at these points. The angle phi is given by the relation tan phi equal to r d theta dr. And so trace the cardioid r equal to a 1 plus cos theta. This is the example, and we are going to trace it. What it looks like in geometry, r equal to a into 1 plus of cos of theta. It is sometimes called cardioid, right? So solution, let me give you the solution first. So we have to check first symmetry, isn't it? The first one is the symmetry one, second one is the region, and third one is the angle between this one. So firstly symmetry, put theta equal to minus theta, and this will be cos theta equal to minus of cos theta, cos of minus theta. So cos theta does not change in the fourth coordinate, so cos of minus theta. So that means it does not change, that means it is symmetrical about the initial line, right? Initial line. So this one is the symmetrical about the initial line. That means we need to trace the curve only above the initial line or below the initial line, and then do the symmetry and exactly equivalent shape of the curve in the other side, below or above. Rest half curve would be the reflection along the initial line. Region, and cos theta has the maximum value as minus 1 to plus 1. It lies between where? Cos theta lying between less than 1, right? Therefore, the curve lies inside the circle r equal to 2a. See here. So how much the maximum value? R equal to cos theta is equal to 1. So a plus a equal to 2a. So the maximum value is r equal to 2a. Now tangent. For tangent, you need dr by d theta. Dr by d theta is equal to minus a sin theta, and hence dr by d theta is less than 0 when 0 theta to pi. Thus r decreases as theta increases in the interval 0 to pi by 2. Similarly, r increases when theta in pi by 2 to theta. So we had find out the three properties for that. The tangents which as r decreases as theta increases, and r increases when theta in pi by 2 to theta. So here we have theta and is 0, then r equal to 2a, pi by 2, then it is equal to a, and pi is equal to 0. And we have seen that for 0 to pi by 2, r decreases as theta increases 0 to pi by 2, and pi by 2 to pi, r increases, right, with theta. So this is the increasing, r also increases with theta, and here r decreases with theta, right. So combining the facts that we can easily draw the graph above the initial line. By reflecting this portion in the initial line, we complete the graph, and if we allow A to vary and keep is positive, then the size of the cardioid varies. If A is negative, the cardioid changes its directions. So now do the same thing. So here we had the maximum, it has to be R equal to 2A, R equal to 2A, that is the region maximum, and try to find out the initial line F up to the initial line. So this is the initial line, and as you can see, R increases or decreases. See, R decreases in where? Theta to pi by 0 to pi by 2 with the theta. So this is pi by 2 here, this is the pi by 2 here, this is pi by 2 here, and with the theta increases, R decreases. So the R1 is the maximum value, this one is the maximum value, then R2 is the minimum, less than. So R1 is greater than, R2 is greater than, R3 is greater than, so on, till when? Pi by 2, till theta become pi by 2. So this one, so this means this is the maximum value and it's going to be decreases. But as it's going to pi by 2 to pi, R increases with the pi by 2. So that means this is going to be a hard type of the shape. Similarly, now we can have the symmetry. So with the symmetry, this function is like this. Now if I change a value of A, then the directions and as well as their shapes are identically changes, and if A tends to negative, then it changes the direction as well. So here we have A equal to 1, 2, 5 and minus 1 here. So for minus 1 is here, as you can see, this is the changes their direction in the left hand side, and for A equal to 1 is here, and as you can increase, this will be increases, A equal to 2 and this is A equal to 5, so bigger one. Similarly, you will have A equal to minus 1, A equal to minus 2 here, minus 2 here, A equal to minus 5 here, and so on, right. So these are the curve tracing, and we had traced the cardioid very successfully by using three properties. First one is the symmetry, second one is the region, identified the region, the third one is the tangents, and these gives me the idea how the cardioid has the shape. Now look at the next example, which are also very spiral form and which is very important. So trace the equiangular spiral R equal to A E theta cot alpha. So let us firstly define for region. So region when theta equal to 0, this will become 1, theta equal to 0, this will become 0 into cot of alpha, and that will become 1 by minus of this, so that will become 1, right. So this whole become 1, so R equal to A, right. So as theta equal to 0, R equal to A. Symmetry, obviously there is no symmetry, change theta equal to minus theta and it will comes out to be R equal to A E of minus theta cot alpha, which is not the same as R, right, which is not the same as R, which is not the same as R. So that means there is no symmetry at all. You can change R as well and you will see that this is not the same one. So equation has been changed with the theta and R as well. Tangents, now find out the tangents. So for the tangents you need to calculate dr by d theta, right, and once you have a dr by d theta, that will gives you in which direction it increases and in which direction it decreases. So if I put dr by d theta is here is equal to A E theta cot alpha into cot alpha. So that means R into cot alpha, right? Write down. And it is always positive, R is greater than 0, cot alpha is also positive. So which is positive, assuming cot alpha is greater than 0, and hence as theta increases, so does R, and R d theta by dr equal to tan alpha. Thus at every point the angle between the line joining a point on the curve to the origin and the tangent is the same, namely alpha. So it is the alpha only, right. So doing the same thing, we understood the three properties. The first one is the region when theta equal to 0, R equal to A. When symmetry, there is no symmetry at all, and the tangents, we had seen that dr by theta equal to r cot alpha, and it is going to be positive if I remain in the cot alpha is greater than 0, and that means it is increases with the theta as well. So, r increases with the theta. Thus, at every point, the angle between the line joining a point on the curve to the origin and the tangent is the same as alpha. See, every point joining of this one. So, that means it is nothing but it is going to be a spiral one. So, the angular spiral r equal to a e theta cot alpha is known as the curve of the pursuit, and suppose 4 dots start from the 4 corners of a square, something like here. So, this is the 4 corners of the square is here, and suppose these are the dots, and they will start, suppose 4 dots start from the 4 corners of a square, each pursue the dog in front with the same uniform velocity, always following the dog in front, then each will describe an angular spiral, isn't it? See, like this, you will see like that means it's the here, and then it will here, and then it will be here, and then it will be here, right? So, several shells and fossils have forms which are quite close to the equiangular spirals. I mean, for the historical point of view and biological point of view, what we had seen is the several shells and fossils have forms which are quite close to the angular spiral. Seeds in the sunflower or blades of a pine cones are also arranged in this form, right. So, you have seen the sunflower or blades of the pine cones, as you can see in their spiral form. So, our curve r equal to a e theta cot alpha is an important not only for the geometrical things, but it is also in a frequently find in different type of the biological and historical implications and applications. Now, look at this example, the third example, trace the curve r equal to a sin theta. We are going to check 3 properties. First one is the symmetry, the second one is the region, and third one is the tangent in the polar form to trace a curve, right. So, let us decide region. How much the value of sin 3 theta? Any value of sin of x is always less than or equal to 1 and greater than or equal to minus 1. Without worrying about how much the x it has, means without anything we can say directly that sin of anything is within the minus 1 to 1, isn't it? I mean, you can go through this one and you will see the, you will see like this, right. So, it is within the minus 1 to minus 1, right. So, sin of 3 theta here has the maximum value how much? Maximum value is 1. So, r equal to a is the maximum region where the curve lies inside those circle. So, you have r equal to a, something like this, and we are looking for the curve inside this a, right. So, the area, the radius is a r equal to a, and inside those area the curve lies, each point of the curve lies. The origin lies on the curve, because if you put this is the only point where the initial line meets the curve, isn't it? So, symmetry, there is symmetry about the line theta equal to pi by 2. Let us put the theta equal to pi by 2, as the equation is unchanged. If I put theta equal to minus, so r equal to a sin of 3 theta, and I want to change this theta by pi minus of theta. So, that this become r equal to a sin of 3 into pi minus of theta. So, this will become a sin of 3 pi minus of 3 theta, and 3 pi minus of theta, that means see here, this one is the pi, this one is the 2 pi, and this one is the pi, right. So, 3 pi minus 3 theta is equal to the same number, right. So, this will becomes out to be a of sin 3 theta. So, this will be r. So, by changing theta to pi minus theta, the equation in a polar form remains unchanged, and henceforth it is symmetrical about theta equal to pi by 2. Theta equal to pi by 2 is a line in a polar coordinates passing from the pole and tangent to the initial line itself. So, normal to the initial line actually, right. So, theta equal to pi by 2 as a symmetry, it has a symmetry. Tangents now. So, r equal to 0, theta equal to n pi by 3, where n is any integer, hence the origin is a multiple point. The lines theta equal to 0, pi by 2, 2 pi by 3, pi, 4 pi by 3, 5 pi by 3 and 2 pi, it is see being tangents at the pole. Monotonicity. For monotonicity, we have to find out dr by d theta. Calculate dr by d theta, that will give you 3 cos of 3 theta, right. See, taking the value a equal to this one. So, hence r increases in the interval 0 to pi by 6, pi by 2 to pi by 6 and 7 pi by 6 to 3 pi by 2, and decreases in the interval pi by 6 to pi by 2 and 5 pi by 6 to 7 pi by 6 and 3 pi by 2, 5 pi by 3. Notice that r is negative when theta belongs to pi by 3 to 2 pi by 3, or theta belongs to pi to 4 pi by 3 or 5 pi by 3 to 2 pi, right. So, these are the monotonicity, hence the curve consists of 3 loops as shown in the figure. The function is periodic and the curve retraces itself as theta increases from 2 pi onwards. Here it is. So, there are 3 loops as we had seen here, 3 into this one. So, here are the 3 loops, and these lines depends separated the whole 3 loops in a different way. So, in a polar coordinates, equation of the form r equal to a sin n theta and r equal to a cos n theta, in which a is greater than 0 and n is a positive integer, represent families of flower shaped curves called roses. So, r equal to a sin of n theta is the roses, right. Consist of n equally spaced petals of the radius a, n petals, right, equally spaced with the radius. How much? The radius is r equal to a. If n is odd and 2n, this is the n petals when n is odd, and 2n equally spaced petals of radius a if a is even, n is even. So, you have a r equal to a sin of 2 theta and r equal to a of sin of 3 theta. Both have a different type of the petals. The first one r equal to a sin 2 theta, when n is equal is this one r equal to a sin 3 theta, it has the n petals only, and it has r equal to a as a circle, right. Here it has the 2n, that means it has the, so that means it has a 3 loops only, petals here, petals means loops, right, something like this. So, it has a 3 loops, and here it has the a sin 2 theta has the 4 loops, 4 petals. So, it is a twice of that even number. So, this is the 2, and if you have a sin 4 theta, it has the 8 loops. So, it's look like something like this, 1, 2, 3, 4, and this is the a sin of 2 theta. But if you increase sin 3 theta, this will become the 3 only, and if you increase here as a 4 theta, it will comes out to be 8 1. But if you increase the 5 1, this will comes out to be the 5 1, right. So, for n is odd, it will gives you n equally when n 2n equally spaced when n is even. It can be shown that a rose with an even number of petals is stressed out exactly once as theta varies over the interval 0 to pi by 2, and a rose with an odd number of petals is stressed about exactly once as theta varies over the interval 0 to pi, right. So, depending on 0 to pi and 0 to 2 pi, it has their own qualitative behavior. Now, this one will be the last example of this course and this domain. Sketch the graph of the function y equal to 1 by x, right? It is given. So, domain and range are fixed. I mean, domain is r minus of 0 and range is, you can say, non-zero number, right? So, symmetrical here fx equal to minus fx is not hold. Thus, the curve is not symmetrical about the y axis. Also, it is symmetrical about the origin and hence it is sufficient to trace it in the first quadrant and rotate this through 180 degree to get the portion of the curve in the third quadrant. Similarly, what will be the interval of increasing or decreasing? So, for increasing or decreasing of a function, you need to find out the first derivative and check whether it is greater than 0 or whether it is less than 0. So, dy by dx equal to minus 1 by x square, which is always less than 0, isn't it? Minus is here, so it is always less than 0. Whatever the domain x is, it does not matter, x belongs to r minus 0, that is all. And hence, as x increases, y decreases. Now, asymptotes, find the asymptotes limit, taking limit 1 by x, x tends to 0, y equal to 0 is the horizontal asymptote and x equal to 0 is the vertical asymptotes, and relative extrema and minima, there is no extrema and minima. So, this will be your first tracing of that graph, right? And as you can see, this is oblique. So, considering all these points can be curved in the first quadrant and gives the complete curve. So, this will be the curve. So, the vertical axis become the asymptotes and this x axis, horizontal axis become the horizontal asymptote for this curve. These are the one of another example where you will find y equal to x cube plus x square. Just do the domain and range are r itself, there is nothing to do. Symmetry, the function is neither even, I mean you can see here 3 and 2, so there is no symmetry at all. Points of intersection, you will see this is the point of intersection, minus 1 to 0 put here. 0, 0 is one of the point and minus 1 and 0 is also the point. Tangents, we have a 3x square plus 2x. So, the x axis is the tangent to the origin is equal to 0. So, dy by dx equal to 1 when x equal to minus 1. Therefore, tangent at minus 1 and 0 makes an angle 45 degree with the x axis. And then we will have a relative maxima and minima. We have a relative maximum at x equal to minus 2 by 3 and the relative minimum at 0. And the point of inflection is x equal to minus 1 by 3, changes its sign. So, interval of decreasing and increasing, we can calculate it and then we can find out the asymptotes. So, this is the asymptotes, oblique asymptotes we had here, right? And once we have, then the curve of x cube y equal to x cube plus of x square looks like this. The whole curve is going to be this, right? Similarly, sketch the graph of the function. I think I will left you for this is as an assignment. So, just go through it, even though it has been already elaborated here, but take this one as an assignment and I believe that this will be the end of this course and hope that you will go each lecture of the each week and it will enhance your concepts in a calculus of a single variable. So, thank you so much.